Good afternoon, ladies and gentlemen. I hope you are all doing well and you're all healthy. And before I start the class, let me just tell you something about your quiz. Okay, let me get my pen first. All right. Okay. So guys, last Monday you had quiz. All right. You have another quiz next week. We will see. Maybe Monday or Tuesday or Wednesday. Let's see, after we finish this chapter, I will let you know about the date. Okay. And most probably you will have quiz next Friday or next Thursday. We'll see. So about the quiz, I just received 2 or 3 messages in Telegram. Okay. If you have any objection or and suppose that there was a mistake in the question or in the answer, all right, you need to screenshot and put the question number, all right, and after that you need to email to me. If you send this message to Telegram, I do not accept any message related to this, let's say, official things like quizzes or midterm or exam or assignment. I can't because in Telegram, controlling is very hard. And you are like, how many students? I'm teaching more than 60, 70 students and receiving even 10, 15 messages, right? When I open this immediately, I cannot make a change. But if you send it to my email, it is there. That is official. Okay. I just have a look. And after that, change this or update your score. After that, I close that email. Okay. That is one thing about, what is it? About your quiz. And now you got used to, how to say, online quizzes, online exam. Okay. And also my methods you must be familiar so far. Usually if I'm asking, for example, let's say multiple choice question, you need to put only one letter. So as I told you, as I mentioned in the group chats, even if you just like leave one space bar, it will be wrong because the computer accepts this as a character. That's why it will be wrong. And it just put one letter, that's it. If there are no options, it's not multiple choice question, then just you need to write the numerical value of the question. Because if I ask, for example, let's say you'll talk about the distance. If you write kilometer, some people write kilometer without leaving it in a space. Some people, they just write kilometer in British English, some people in American English. That's confusing. The system does not allow me to add these conditions. That's why you need to write only numerical value. I already mentioned it is a unit in the question. Okay. All right, that's it. Another more important thing here is if you have any objection or any question, you need to bring to the class. All right. If you just drop this, okay, Mr. Cost, you made a mistake, blah blah blah. Okay, first tell me here that I can correct this immediately. Okay. All right, guys. Today we will continue again. We will talk about integration. That is not a long chapter; it is a short chapter. And this week I'm going to finish this. Maybe tomorrow. And I heard that on Friday you have state exam. At that time, you need to practice these questions. We will see. Okay, but today and tomorrow we are going to finish this chapter. And last time we were talking about definite integrals, and also a few things were left. And let me just talk about one important theorem and move on. What we have here, that's one important theorem: average value of a continuous function revisited. Okay, so revisited means at the beginning of this chapter, actually, we just give some idea how to find the average value. When we talk about the average value of a bunch of numbers or a collection of numbers, usually how do you do this? The definition is simple, right? We just add the numbers together and divide by the, what is it, divided by the number of data, number of numbers there. For example, if you want to find the average quiz score of a group of students, we should just add all of their quizzes and divide by the number of students. That gives us, what is it, the average value of those numbers. But here, when we talk about continuous function and over the interval, for example, AB, since it is continuous, how many points do we have? We have infinitely many, right? And how can we calculate one by one? We cannot calculate this. And that's why actually we have infinitely many points. That actually involves, what is it? A definite integral. But idea, again, it is very simple. So again, using the basic definition, we are going to form our sum, and you will see that we will have a Riemann sum. Actually, we can just turn this into Riemann sum. Suppose that this we are giving as a definition, if f is an integrable on AB, and then its average value on AB is also called its mean, is average value of f is equal to 1 over b minus a times integral from a to b f of x dx. Why is it so? First, if you just choose a few points over the interval AB, right? Let's say we choose n points, okay, and I'm just approximating, and the average value of this function, average value of f over the interval, okay, average value of f over the interval AB can be approximated by this sum. Here we have f, C1, it's the first point, C2, the second point, C3, blah, 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 until Cn. So here we have C1 plus f of C2 dot dot plus f of Cn. And we should just divide, right? These are the values of the function at n different points over the interval AB. They are selected from this interval, and divide by the number of data. How many numbers we have here? We have n, right? So if I just divide this, in this way we can estimate, we can approximate the average value of this function. And now how actually accurate is it? It depends on our number of points, how many points we are taking. If we take more and more points, it gives us better and better result. So now if you just look at this, again, I can just write this in compact form, right? Here we have 1 over n, take this out, and f of c1, f of c2, f of cn, just using sigma notation. Here we have sigma, k is from 1 to n, and here we have f of c sub k, right? So now if you just look one interval, all right, suppose that they are equally spaced, for example, let's say, if you just look one interval, right, that is from, what is it, c sub k minus 1 to c sub k. Okay, let's say the length of this interval is delta x, and all intervals are the same. Suppose that they are equally spaced. Actually, it does not change anything, because when n goes to infinity, after all, the space between any 2 points will be very, very small, almost zero. Okay, so at that time, we just divide this AB, right, interval AB into n subintervals. The length of this delta x will be the length of the interval, that is b minus a, and divide this by n, right? And that is the length of one subinterval. Now from here, just doing simple algebraic manipulation, I can actually find or express 1 over n in terms of the remaining variable. So from here, what is 1 over n? 1 over n is equal to delta x over b minus a. So instead of 1 over n, I'm going to write this expression. So equals here 1 over n, that is delta x over b minus a. And here we have sigma k equals 1 to n. And here we have f of c sub k. So now delta x, it is a constant number. I can bring inside the sigma. Then here we have 1 over b minus a, right? Here we have sigma k equals 1 to n f of c sub k times delta x. Okay, so now even you can just write here delta x here, but here I'm just choosing this as a constant number. All right. So what happens here? Well, you see here inside the sigma, we have the value of the function, right? F at some different points, f of c1, c2, c3. And here we have delta x. What is this? It's just exactly the Riemann sum, right? So the interval length and multiplying by the value of the function at some point taken from that interval. So that means that if we increase the number of points here, it gives us better approximation. How about if n goes to infinity? When n goes to infinity, it gives us actually the exact value, I mean the exact average value of f over this interval. So we know that when n goes to infinity, this 1 over b minus a, it's a constant number. So this sum, right, actually it's opposed to this thing. What is it? Just integral from a to b. Here we have f of x dx. And that's why actually we are defining the average value of f over the interval AB as b minus a times integral from a to b f of x dx. Soon we will use this because that theorem is really important to prove the fundamental theorem of calculus. That's why we need to understand the main idea there. For example, find the average value of f of x equals 4 minus x squared on negative 2, right? And so here, what is this? F of x, right? If it is y is equal to square root of 4 minus x squared, which means that here y is positive. It just gives us the semicircle, right? The semicircle that is located above the x-axis, right? And now here by average value theorem, we are saying that, okay, we are saying that if we have a rectangle here whose length is equal to the length of AB, that is negative 2 to 2, that's equal to 4. And if you just multiply, find the area of the rectangle, that is equal to the area of the region which is bounded by the graph of this function, okay? It's like, how am I going to say, because if you just imagine that we have a kind of water, right? And if you just put this some kind of rectangular tank, it will be certain height. That height will be between 0 and 2. So anyway, find the average value of f. How do you find the average value of f? Average value of f is equal to 1 over the length of the interval, that is 2 minus 2, that's equal to 4, integral from negative 2 to 2. And here we have f of x, that's equal to 4 minus x squared and dx. Okay. So now we know that from negative 2 to 2, 4 minus x squared, the function is positive, and this definite integral gives the area. Because right now we are not in the position of calculating this kind of integral. We have not studied yet. We will study a bit later in chapter 6, right? So now just using the definition, since it gives us the area, we know how to find the area of a semicircle, right? 1 over 4. What is the area of the semicircle whose radius is 2? That's equal to 1 over 2, because semicircle, pi times r squared. The radius is 2 squared, which is equal to pi over 2. So at the time, the average value of the function is pi over 2. That means that actually I can construct a rectangular container, let's say here, whose height is pi over 2 and the length is 4. Actually, it contains the same amount of water, whatever it is, that as the original container, that is semicircular container. Okay, someday everything will make perfect sense. So for now, laugh at the confusion, smile through the tears, and keep reminding yourself that everything happens for a reason. That's also a good quote, especially we are going through a lot of difficult times these days, right? COVID, quarantine, and a lot of shops are closed, and you cannot go to gym, maybe you cannot travel. But I think there must be a reason behind this. We hope everything will be better tomorrow. So right now, we try to use every minute of our time to learn something, to improve ourselves, to make something different, and definitely it will pay off. And sometimes, of course, we get bored. It is another thing. But after all, if you work and if you just give some effort, it will pay off. Guys, let's continue. I will move to the next part of the chapter. We will now talk about the most important theorem of calculus. That's why it's called fundamental theorem of calculus. Before this, we need to prove one important theorem, and after that, we will move to the fundamental theorem, and after that, we'll just speed up. Actually, that speeds up our calculation, because since we have proved this is a kind of rule, or let's say weapon or tool, using this one, we can do a lot of stuff. So 5.4, that is fundamental theorem of calculus. So in this section, we present the fundamental theorem of calculus, which is the central theorem of integral calculus. It connects integration and differentiation, enabling us to compute integrals by using an antiderivative of the integrand function rather than by taking limits of Riemann sums. We did in section 5.3. Anyway, so far, as you see, we have been studying that. Even you know that if you just integrate the function, right, it gives us the capital F. That is the antiderivative of the function. Now, if you differentiate that antiderivative of the function, right, that means that you're differentiating the function, it gives us the original function back. Actually, this fundamental theorem actually gives us a kind of, how to say, it just proves actually that method actually is true in general. If you differentiate the integrated function, it gives us the original function. And if you integrate the original function, that it gives us the capital F. Anyway, now let's start with this theorem, the mean value theorem for definite integral. And also before in chapter 4, we talk about the mean value theorem, right? In general, what is it? If you remember, if you're given a continuous function on AB and it's differentiable at its interior, right? And there is at least one C where f prime of C is equal to f of B minus f of A over B minus A. But here f of B minus f of A, instead of this one, here we have integral. And on the left-hand side, we have, what is it? F of C, not f prime of C. Okay. Why is this so? All right. Once again, if f is continuous on AB, then at some point C in AB, that means that there exists at least one point in AB such that f of C is equal to 1 over B minus A times integral from A to B f of x dx. Okay. And the figure, as you see here, f of A, and that the blue line is the graph of the function, and the average height is f of C. And simply we are saying that the average value is equal to the value of the function, right? Some point in the interval a b. Okay, in the first part of this chapter, we have proved that this integral from a to b, right? F of x dx, it is always greater than or equal to minimum value of f times the length of b minus a, right? And also it is less than or equal to maximum value of f times, let me just write that in parentheses, just one value, minimum value of f, maximum value of f, and here we have b minus a. What does it mean? It means that here always we can just put the region under this curve, and between these two rectangles, it will be between two rectangles. That is the minimum value, and this one is the maximum value, right? The maximum value, it is between these two areas. Okay. Now from here, b minus a, and here a is not equal to b. We are not talking about a single point because a single point, the integral is equal to 0. Now if you divide all sides by b minus a, what we have here? Here we have minimum value of f is less than or equal to 1 over b minus a, integral from a to b, f of x dx less than or equal to, here we have maximum value of f, right? Now, if I just denote this by lowercase m, this maximum value by capital M, if you remember from the first theorem, right, in chapter 3, if you're given a continuous function over the interval AB, then it has global minimum and global maximum. And if this value, 1 over b minus a times integral from a to b f of x dx, if it is changing between the minimum value of f and maximum value of f, that means that then there exists some c in the interval ab. Let me just include, doesn't matter here, where this f of c should be equal to 1 over b minus a from a to b, and here we have f of x dx. Okay, because a continuous function, that means that since it is continuous, that means it's taking all the values between lowercase m and the uppercase m. And if this integral 1 over b minus a times integral from a to b f of x dx is between these two numbers, then there must be some point in the interval ab where f of c is equal to this integral. And that's really important to prove the fundamental theorem. That's why we should understand this well. So actually we will use this again. Show that if f is continuous on AB, and a is not equal to b, and if the integral from a to b f of x dx is equal to 0, then f of x equals 0 at least once in AB. So by using that theorem, right, the previous theorem, now then there exists some c in the interval AB where that's equal to f of c is equal to f of c is equal to 1 over b minus a integral from a to b f of x dx. But in the question, it's given that this integral is equal to 0. So that's equal to 1 over b minus a times 0, which is equal to 0. So that means that if this integral is equal to 0, then there is at least once, actually 1 point in the interval AB where the value of the function is equal to 0. That means that its graph is passing through the origin. Not origin, sorry, it's passing through the x-axis. Okay, now guys, let's talk about the fundamental theorem of calculus part 1. Let me just see if I have enough space. Okay, I don't have enough space, so I'll just add one. All right. Okay. The fundamental theorem of calculus, part 1. It has 2 parts. Now we'll just start with the first part. It says that if f is continuous on AB, then f of x is equal to, from a to x, f of t dt is continuous on AB and differentiable on AB, and its derivative is f of x, that's equal to, what is it? It means that it's antiderivative, right? If you just differentiate this, that is equal to f of x. Okay. What does it mean? It means that first, if you integrate, as I say here, if you integrate our function f, after that, if you just differentiate this, we are getting back our origin function, right? That's what it's trying to say here. So that means that simply that our antiderivative, right? If we differentiate this f, then that's equal to f of x. So that is very important theorem, but until the 17th century, people maybe they didn't need this, or I don't know, the conditions, right? But once they proved this theorem, they discovered this rule, and after that, it's really actually speeded up the development of or advancement of science for the next 200 or 300 years. Okay, now let me just start with this drawing. Suppose that we are talking about a function f. Let me, I should draw a bit longer. Okay, so now we know that if you're given some interval, right, from here, maybe something like this, doesn't matter. Let's say from A to B, okay? And then we are talking about this function that is y is equal to f of t, because now I'm going to use x, that's why I'm using t here. And that's our t-axis, this one is y-axis. Actually here, what actual variable you use, f of t, f of x, f of w, it does not matter, right? The important thing is, what is our function doing here? That's important, okay? And also by using the definition of definite integral, right? So for example, if I just calculate the definite integral from a to b, it gives us the area under this curve, right? And which is bounded by these two vertical lines, x equals a and x equals b, and the x-axis and the curve, right? So now, how about if I just find the area from A to until here, for example? Let's say we are talking about this area. And this point, let's say it is not a fixed point. It may change. It may change it may assume any value between A and B. So that means that at the time, this area under this curve, it will be a function of x because it depends on x, right? If it is somewhere, for example, in the middle, for example, it gives a different area. Anyway, if you just give different value to x, it gives us different areas here. Okay. So at the time, what is f of x then? Here, f of x, this capital F of x is equal to the area from a to x, right? Our function f of t, and here we have dt. Again, a lot of students may confuse Mr. Custom. Actually, we're talking about x. Why are you using t? I can use x here actually, but here I have already used this x here. That's why if I wrote one more x, you get confused. Okay, this x and this x, they represent different things. But actually, again, f of t, this f of x equals x squared, f of t equals t squared, f of z is equal to z squared. They are exactly the same functions, right? And we can just use any variable. Okay, using different variable, it does not change the nature of the function. Anyway, so Now from here, all right, we know that from here f of x, what happens if you just differentiate this function then, right? So that means that if you differentiate this function, because this one is f is the antiderivative, right? Now from here, if you differentiate d f of x, right? So we're saying that that's equal to f of x. Okay, so that's what, sorry, it's not like that. So now we are going to show that here, if you differentiate this f of x, capital F of x, that's equal to f of x. Our task is this, actually, because here, as you see here, I'm going to prove that f prime of x, that's equal to f of x. Okay. Again, here we are just going to use the area formula again. Okay, just the the definition of what is it? The definite integral. All right. Now from here, if I just move this x, for example, to another point, suppose that let me just use another different color here. If I just move this here, I'm just doing a bit bigger, okay, so they can see easier. Let's say this point is x plus h, okay. So then what will be this green shaded region then? And that it will be the area from a to x plus h minus the area from a to x, right? So at the time, this green shaded region, it will be equal to that actual, that area, what is it? That area is, um actually that's equal to f of x plus h, right? Minus f of x, right? So if you just approximate here, what is this? It is, I can just approximate this with this thing, right? It is, I just choose one point, the value of the function, and it's approximately equal to the length of the rectangle, which is equal to h times, here we have f of x. Okay. So now from here, if you just divide both sides by h, then at the time I will have this one, x plus h minus f of x over, here we have h is approximately f of x. Now, what happens actually if this h, what is it, approach 0? At the time on the left-hand side, right, on the left-hand side, what is it if we have just the integral, right? Sorry, on the left hand side, if h approaches 0, f of x plus h minus f of x over h, that's just the derivative of capital F, right? And as h approaches 0, it gives us better approximation of the area, the f of x, right? Which means that here, if h goes to 0, then on the left hand side I have f prime, on the right hand side we have f. And that's why actually here we have f prime of x is equal to f of x. Okay. On the other hand, if we just continue actually proving, how to say, using this, because we didn't use the average value of the function here, how we are going to use the average value of the function here. So now we are going to prove this. Okay, so first I'm going to prove that this f of x plus h minus f of x over h, right? When h goes to 0, that's equal to f of x. All right, why is this so? So now if you just take the limit of this function as h approaches 0, so that is equal to what we have here. Let me just write it as limit as h approaches 0. Take this h out. And here we have f of x plus h. What is f of x plus h? F of x plus h is here, right? Actually, we are talking about the whole big reason, the triangle. Sorry, the region. So anyway, so that thing is f of x plus h is the area from a to x plus h, and here we have f of t dt, right? Minus, how about f of x? See here, f of x is the area under the curve from a to x. So that is definite integral from a to x. Here we have f of t and the dt. Now I can just separate this one, a to x plus h. I can just write it as limits as h approaches 0, 1 over h. And here I can write it as from a to x, f of t dt plus, and from x to x plus h. f of t and dt. And minus still I have one more integral here from a to x. Here we have f of t dt. Now these two things are the same, right? It is just the area from x to x plus h. Again, we are just talking about this green shaded area here. So that's equal to from x to x plus h, right? And that's equal to, what is it? That thing. Integral from x to x plus h f of t dt. And also divided by h. So now, using that mean value theorem, right? So actually, if I just apply this there, then there exists some c over the interval from x to x plus h, where f of c is equal to the average value of this function. What does it mean? Now let me just keep this here. So we have here h approach 0, 1 over h. Actually, this h is, what is it? X plus h minus x, right? And how about here? Here we have integral from x to x plus h f of t dt. And exactly we have here, what we have here? We have here b minus a, that is the integral. I'm just talking about this small region, right? I'll talk about this one. This point is x. This one is x plus h. And this function is f of t, right? So now I'm saying that there exists some c in on this interval where f of c is equal to this integral. So that's equal to limit, and as h approaches 0, and here we have, come on, and here we have f of c. Okay, continues. And what happens to c if h approaches 0? If h approaches 0, right, and c is trapped between x and x plus h, and automatically also that c approaches x, and also c must approach x because it is a continuous function, and c is a point between x and x plus h. If h approaches 0, that means that the distance between x and x plus h is getting smaller and smaller. It's approaching 0, which is just pushing c towards x. And finally, eventually also c actually gets very close to h, even closer to to x than h, which means that since it is a continuous function, when c approaches x, this thing is equal to x. On the left-hand side, as you see here, I have f prime of x. On the right-hand side, we have the original function. All right, guys, let's have some rest, 10 minutes, okay? After 10 minutes, we will use them to solve some questions. I will see you after 10 minutes.